Hello and welcome to the second video of example first order decay problems. In this example, we're going to estimate the concentration at a certain time in the past. Here's the setup. An accident caused a sudden release of carbon monoxide into the indoor air of a research lab. First responders arrived in 15 minutes and they measured CO levels when they arrived of approximately 10 part per million by volume. The laboratory has an air exchange rate of 8 per hour. It's pretty typical of some labs. And our task is to estimate the peak CO concentration at the time of the release, so the starting concentration. We can assume first order kinetics is typical of indoor air with and air exchange rates. So let's go ahead. So let's first start by writing down our first order decay equation. Ct equals C naught e to the negative kt. So we are interested in C naught. So we want to solve this equation for C naught. So I'm just going to rearrange a little bit. C naught is equal to concentration at some time T over e to the negative kt. Alright, do we have everything we need? Concentration at some time T, yes, that's our 10 part per million. The decay rate, first order decay rate, yes, 8 per hour. Elapsed time, yes, 15 minutes. So we have all that. So let's just go ahead and plug in those values. 10 part per million over e to the negative kt, that's 8 per hour, multiplied by the elapsed time, which is 0.25 hours. Just going to carry that out. So we end up with 10 over 0.135. And from that, get a concentration of, I have it right in front of me, let's see, 10 divided by 0.135. So we get about 74 part per million. So based on these conditions and assumptions, we estimate a peak concentration of 74 part per million. Is that concentration high or low compared to the known dose response curve or relationship for CO? Leave that to you to look up, but the short answer is it's pretty high.